Log on, tune in, find out. Another good idea from Cambridge.
Seminar talk by Lok Ming Lui from Chinese University of Hong Kong, and he will talk about computational quasiconformal geometry, a tool for medical morphometry, computer graphics, and vision. Please.
So first of all, I'd like to thank the organizer for inviting me to this wonderful workshop in this beautiful campus. Actually, it's really good to visit Cambridge again because my wife actually studied here before, so we had lots of nice memory here. So anyway, the title of my talk today is Computational Quasiconformal Geometry. I call it a tool for medical shape analysis, computer graphics, and visions. So this is actually part 2 of a sequence of 2 talks. The first one was already presented by Professor Tony Chan, that he gave a really nice overview of both conformal and quasi-conformal geometry in medical imaging applications. So today I'm going to focus on computational quasi-conformal geometry, and then I'm going to show some more application in medical imaging. So this is a joint work with Professor Tony Chan, who was my PhD advisor when I was at UCLA. Professor Xing-Tung Yao, who was my supervisor when I was a postdoc at Harvard, and Professor David Gu, who is now in Stony Brook University, and Dr. Alvin Wong, who is now in UCI. So this is the organization of my talk. So first of all, I would like to give you the motivation of our research. Then I'm going to talk about how we can build a discrete analogs of quasi-conformal geometry on discrete triangulation meshes. Because in practice, all surfaces that we encounter are represented discretely by triangulation mesh. So it's very important for us to have a discrete analogs of QC geometry on triangulation meshes. And then it turns out that this definition of discrete QC geometry on meshes will lead to a very effective algorithm to compute quasi-conformal mapping between survey meshes. And then I'm going to show some more application of QC theory. So we have already heard about a lot of different type of application of QC theory in medical imaging. For example, Tony has already mentioned some of them, and Professor Estella has also mentioned how QC geometry can be used for inverse problem. So today I'm going to focus on more imaging application and computer graphics applications. So motivations. So our research was actually motivated by practical problems in imaging, graphics, and visions. So what we're interested to do include, for example, data processing, in which, for example, if we have some surface, like the brain surface, usually the surface that we obtain are very noisy, so we have to do some data processing on it that preserve the geometric details of the data. We also want to do registration between different surfaces so as to find one-to-one correspondence between them so that systematic analysis can be carried out. We're also interested in doing shape analysis. So after we get the registration, we also want to have some type of quantitative measurements to study the shapes. So for example, Mario has already talked about how we can define some distance between shapes. So this is really nice. So we also are interested in working on these type of problems. And we're also interested in doing different type of image processing on surface. For example, compression of the registration that I'm going to talk about, in-painting, texture refinement, and so on. So it turns out that all these applications are very related to geometry. So this motivates us to look for some differential geometry techniques to solve these problems. So it turns out that computational quasi-conformal geometry, which basically study the deformation patterns between shapes, is an ideal tool for these purposes. And today I'm going to focus on looking at how computational quasi-conformal geometry can help solving this problem. So I guess Tony has already given us a very nice overview of what quasi-conformal geometry is. So just a recap, quasi-conformal mapping is a generalization of conformal mapping, so which is an orientation preserving homeomorphism between surfaces with bounded conformality distortions. So intuitively, conformal mapping map infinitesimal circles to infinitesimal circles, whereas quasi-conformal mapping will map infinitesimal circles to infinitesimal ellipse. So for example, here we have a hippocampus surface, which is a subcortical structure inside the brain. So it's very important for us to analyze this structure. So if we parameterize the hippocampus onto the 2D parameter domain conformally, And then on the parameter domain, we draw some circle packing patterns and project it back to the surface. You see that under conformal map, the infinitesimal circle will map it to infinitesimal circles. But under quasi-conformal mapping, infinitesimal circle will be mapped to infinitesimal ellipse. And then it turns out that this, the distortion from circle to ellipse is measured by something called Beltrami coefficient mu. And mathematically, quasi-conformal mapping satisfies this Beltrami equation. And mu is the measure for the conformality distortion. So in our work, we mainly focus on looking at this mu to represent the diffeomorphism and to control the diffeomorphism and to study the deformation patterns between shapes. So just to recap, so Tony has mentioned some of the applications of quasi-conformal geometries. So one of the applications that he mentioned is that we can manipulate, we can control the mu to find a geometric matching registration between hippocampus surface. So he also talked about how we can use the Beltrami coefficient to do shape analysis of the brain cortical surface to study the gyrification patterns on the brain. So combining the Beltrami coefficient with the curvatures, we can also define a complete shape index which measure the detailed geometric difference between surfaces. So these are some of the applications that Tony has mentioned. So, but the question is, most of the existing theories that we have mentioned about quasi-conformal mapping are defined on continuous smooth surface. So in practice, most of all the surfaces that we are looking at are discrete triangulation meshes. So it is very important for us to have the definition of discrete quasi-conformal so that we can do some analysis. So one of our very first goal in our project is actually to give a discrete definitions of quasi-conformal geometry on triangulation meshes, which is, first of all, well-defined, and secondly, it should be analogous to the continuous case, so that the theories in the continuous setting can be applied to the discrete setting. So it turns out that we can do so by looking at the matrix representation of conformal and quasi-conformal. So just to recap, under conformal mapping, the matrix representation is as follows. The pullback matrix is equal to the background matrix up to a scalar multiplication of the conformal factor lambda. But under quasi-conformal mapping, the pullback matrix is equal to some scalar multiplied by the distorted matrix, and the distortion is given by this Beltrami coefficient mu. Okay, so it turns out that we are going to use this matrix representation to define the quasi-conformal geometry on discrete triangulation mesh. So now I'm going to briefly describe how we can define a discrete quasi-conformal geometry on triangulation meshes. So in order to define a discrete analog of quasi-conformal mapping on discrete triangulation mesh, so we have to look at one observations about quasi-conformal mapping between surfaces, so smooth surfaces. So before we go into the discrete case, so let's first of all look at the continuous case, the smooth case. So suppose we have two Riemann surfaces S1 and S2 with Riemannian matrix G1 and G2. So suppose we have a quasi-conformal mapping between them, between the two surfaces, associated with some Beltrami coefficient mu. Okay. So the theorem basically says that we can distort the matrix on the original surface S1 associated with the Beltrami coefficient mu. Then under this distorted matrix, this quasi-conformal mapping is actually conformal. Okay. So the key ideas of this theorem is that we can convert the quasi-conformal map into conformal map under suitable distorted matrix. So the idea is actually very simple. If you go back to the metric definitions of quasi-conformal mapping and conformal mapping, we see that under conformal mapping, the pullback matrix is equal to some scalar multiplied by the background matrix. But under the quasi-conformal mapping, the pullback matrix is also equal to some scalar multiplied by some distorted matrix. But if we consider this whole thing to be our matrix on the surface, then essentially the pullback matrix is equal to some scalar multiplied by the matrix. In other words, this is conformal. So the key here is that we would like to convert everything into conformal because we have the whole theories about conformal on the discrete case. So if we want to study the quasi-conformal and define a discrete analog on triangulation mesh about quasi-conformal, the best way is to convert it into a conformal setting. So this is the idea. So of course, if we want to use this observation to define discrete quasi-conformal, first of all, we have to define what is a matrix on a triangulation mesh. And then after that, we have to define what is the discrete conformal on the triangulation mesh. So it turns out that the definition of discrete matrix and discrete conformal can be very simple. So first of all, a discrete matrix defined on the triangulation mesh is basically just a positive value function defined on each edge that satisfies the triangle inequality. So essentially, the matrix is just the length. You give the length on each edge that satisfies the triangle inequality. So with the discrete matrix, now we can define what a discrete conformal deformation is. So suppose we have a mapping between two triangulation meshes, and suppose on this mesh, the discrete matrix is lit to L, which is the length on triangulation mesh. And then on this mesh, the matrix is capital L. Then we define a mapping between these two triangulation meshes to be discrete conformal if there exists a function u defined on each vertex, such that the capital L is equal to lit to L up to a scalar multiplication of exponential u. So this is similar to the definitions of conformal in the continuous case, because in the continuous case, conformal mapping preserves the matrix, so up to a scalar multiplication of the conformal factors. So this function defined on each vertex is like the discrete conformal factors on triangulation mesh. So now with these definitions of our discrete matrix and discrete conformal deformation, now we can give the definitions of discrete quasi-conformal using the observation that we saw. So basically, the idea is that we define quasi-conformal as conformal under the suitable matrix. So basically, we say that okay, we have a mapping between two triangulation meshes. We call this mapping to be a quasi-conformal with respect to some Beltrami coefficient mu if the mapping is conformal under the distorted matrix. So we have a distort the length of each edges based on the Beltrami coefficient. Then this is how we define the discrete quasi-conformal mapping on the triangulation mesh. So it turns out this definition is first of all well defined, and also it's good in the sense that we can prove that the discrete quasi-conformal mapping will converge to the continuous quasi-conformal mapping as the mesh size tends to 0. So this is good because then a lot of continuous QC theories can be extended to the discrete case. So another reason, so you may wonder why we define the discrete quasi-conformal mapping in such a fancy setting. So one of the main reasons for us to define it in this way is that this discrete definition of quasi-conformal mapping would lead to a effective algorithm to compute the quasi-conformal mapping. So the basic idea is that now, if you want to compute a quasi-conformal mapping, what we need to do is just to compute a conformal mapping by distorting the matrix. And then we have different algorithms to compute a conformal mapping. So Tony has mentioned some of them. So one of the effective algorithms is to use the curvature flow method. So that's how we compute a discrete quasi-conformal mapping. So I call it the discrete quasi-Yamabe flow method because I'm going to use the Yamabe flow method to compute the conformal map so that we get a quasi-conformal map. So basically, there's two steps. It's very simple. First of all, given a Beltrami coefficient, I distort the original matrix by the Beltrami coefficient, and then we compute the conformal mapping under this distorted matrix using the curvature flow method. So the curvature flow method basically, the idea is to distort the matrix on the original surface to a uniformization matrix, such that under this uniformization matrix, the Gaussian curvature is equal to the target curvature that you want. For example, if you want to flatten the surface, then you have to put k bar to be 0 to flatten the surface. So this is how we compute the quasi-conformal mapping. The key idea to take home is distort the matrix and then compute the quasi-conformal mapping under the distorted matrix. So we can prove the convergency of the discrete quasi-Yamabe flow method. More specifically, the discrete matrix will converge exponentially fast to a discrete uniformization matrix under the quasi-Yamabe flow method. So the algorithm actually converges exponentially fast. So one of the benefits.
What are the surgery operations you mentioned there?
Oh, so of course when we do the it is about the curvature flow method. So when we do the curvature flow method, the curvature flow method can only deal with relatively regular triangulation. That is, the angle of the triangle cannot be too small. If it is too small, then it will go to singularity. So when when you run the algorithm, if you have some sort of if the triangle become a little bit small, then you have to do some edge swapping to make it take away do some surgery on the triangulation to make the triangle better. But in practice, we never encounter this kind of situation. Okay, so one of the benefits for this quasi-Yamabe algorithm is that it can deal with surfaces of general topologies. For example, you can look at a surface with multi-connected domain, homogeneous surface. You can also compute a quasi-Yamabe, use the quasi-Yamabe flow method to compute a quasi-conformal mapping. So it is general. So for example, here we have a human face, and then we take away some region, take away the eyes and take away the nose, and then we can compute a quasi-conformal parameterization onto the 2D domain, the punctual disk. So for example, if you give different values of Beltrami coefficient mu, then you can see that the infinitesimal circle will be mapped to infinitesimal ellipse. So this sort of show you our algorithm can deal with simply connected domain, of course, and also can deal with multi-connected domain. So here is another example. We have a surface of genus 1. So we can parameterize the surface quasi-conformally onto the universal covering. So what we need to do is to cut the surface open along the homology basis and then parameterize it using the curvature flow method again. So with different Beltrami coefficients, you can see different distortions from circle to ellipse. So these two examples tells you that the quasi-Yamabe flow method can deal with general surfaces. So this is different from, for example, the Beltrami homomorphic flow method that Tony has mentioned. So that method is good, but it can only deal with a simply connected domain and also or genus 0 surface. But this one can be more general. Okay, so this sort of the idea is how we define a discrete analogs of quasi-conformal mapping on triangulation meshes. So with this, I would like to show you some more applications. Depending on how much time I have, I would like to show you maybe 2 or 3 more applications in medical imaging or computer graphics. So one of the most exciting things, or one of the most useful things about quasi-conformal mapping is that we can manipulate, we can control the diffeomorphism or study the diffeomorphism effectively using something called Beltrami coefficient. So more specifically, fixing any 3-point correspondence, a surface diffeomorphism can be represented by a unique Beltrami coefficient. So in other words, the collections of all surface diffeomorphism has a 1-to-1 correspondence with the collection of all Beltrami coefficients. So the Beltrami representation is good because in terms of numerical computation, it has very few constraints. The only constraint is that the subnorm of it has to be less than 1. Then there's no other constraint. It is basically a complex value function defined on the surface. Okay. So it's different from the coordinate function representation in which you have a lot of constraints. For example, you have to be 1-to-1 onto you have to satisfy the Jacobian constraint. So for example, if you want to adjust a registration, if you want to find a good registration between surfaces, then you have to, if you manipulate the coordinate function, then it is very difficult for us to enforce this constraint. But if we work on this Beltrami coefficient space, then it's very easy for us to enforce this constraint. So here is one example where we have 2 brain surfaces. So this is a healthy brain, and then this is a brain with Williams syndrome disease. And then we try to register them based on the so-called landmark on it. So after that we have the diffeomorphism between them. Then we compute the Beltrami coefficient of the diffeomorphism. The color map here is given by the norm of the Beltrami coefficient, so it gives you the ideas of how big the Beltrami coefficient is. And then from the Beltrami coefficient, we can reconstruct the diffeomorphism. So here is the reconstructed diffeomorphism. So the black dot here, I'm not sure if you can see, the black dot here is actually the original position of the diffeomorphism. So you can see that the reconstructed diffeomorphism closely resembles to the original one. So it means there is a 1-to-1 correspondence between set of diffeomorphism and Beltrami coefficient. So using this Beltrami representation, we apply to different medical imaging applications. So one of this is called, I do this for the compression of diffeomorphism. So the goal is to find a multi-scale representation of diffeomorphism. So for example, for the purpose of compression of registration, or to do multi-scale analysis of deformation patterns. So this is actually motivated by practical problems that the doctor asked us to do from the UCLA Medical School, Lonnie. So in that project, what we need to do is to study the deformation patterns of about 1,000 hippocampus surfaces, and then over different times. So we have many diffeomorphism between surfaces. So the doctor asked us whether we can find some compact or compassed representation of diffeomorphism so that we can easily manipulate the diffeomorphism. And they also asked us whether we can develop some kind of multi-scale representation of diffeomorphism so that they can do some multi-scale analysis. So of course, using the Beltrami representation, we can do it very easily because now we have once we have the diffeomorphism, we can represent the diffeomorphism with the Beltrami coefficient. And then we can use, for example, anything you like, you can use wavelets. And here we use the Fourier decomposition of the Beltrami coefficient into the Fourier series. So the good thing is that if we do the Fourier decomposition, we can easily enforce the constraint. But if we do the Fourier compression on the coordinate function, the diffeomorphic properties of the mapping will be easily lost. So the advantage of using this algorithm is that it can easily preserve the diffeomorphic properties. So for example, if we take away some high frequency coefficient, then we can do compression of the diffeomorphism, or using this formula, we can do some give a multi-scale representation of the diffeomorphism, so that doctor can understand the deformation pattern at a multi-scale level. So here is an example. So we have a healthy hippocampus surface, and then this is a hippocampus. Actually, it's a patient, over different times. So the hippocampus surface is actually deforming, and then we compute the registration between them based on the geometric matching registration that Tony has mentioned. So then we compute the Beltrami coefficient, and then after we compute the Beltrami coefficient, we compress it, and then we use the Fourier series to compress it. So if you put n equal to 5, then you can see that the reconstructed diffeomorphism is quite close to the original one, but you can still see some error. But if we use n equal to 20, you can see that the reconstructed diffeomorphism closely resemble to the original one. So the compression ratio is almost like 100. So we can also deal with more complicated surface. For example, we have brain surface. So this is the same brain surface, a healthy one, an unhealthy one with Williams syndrome disease. Register them, and then we compute the Beltrami coefficient, and then we compress the Beltrami coefficient. And then with a few coefficients, we can reconstruct the diffeomorphism, which closely resemble to the original registration. So this gives us a compressed representation of diffeomorphism so that we can easily do different type of analysis of the medical surface. So this gives you the ideas of why compression of coordinate function doesn't work. So for example, here we do the Fourier compression on the coordinate function of the same registration. So we can see that the diffeomorphic properties of the mapping will easily collapse. And here, for example, we do a Fourier compression of the registration of the hippocampus. And then you can see that the diffeomorphic properties of the registration will be collapsed. So another application of the Beltrami representation is to do quasi-conformal for refinement. So the goal is to refine a diffeomorphism, a coarse diffeomorphism defined on a coarser grid, to a fine diffeomorphism defined on a high resolution grid. So these are lots of applications. For example, we can do coarse to fine registration. So for example, if we want to do registration between two brain surfaces, so if you look at the high resolution surface, it's very time consuming to do the registration. So we can first of all look at the coarser grid, get an initial registration between them, refine it, and then and then we get a better initialization on the finer grid, and then we do some adjustment. So coarse to fine registration, or we can also do some multi-grid based registration. So project the registration problem onto a coarser grid and project it back. And we can also do texture mapping refinement. I'm going to show some example. Again, the algorithm is very simple, so not too much mathematics here. So what we need to do is just, for example, first of all, we have a coarse diffeomorphism. We compute the Beltrami coefficient, define it on the coarse grid, and then we do cubic interpolation, of the Beltrami coefficient onto a finer grid, keeping its value on the coarser grid, and then we reconstruct the surface diffeomorphism from the refined Beltrami coefficient. So the advantage of this is that we can restore the finest diffeomorphism possible with the least amount of data. So let me show you some example. Okay. So we have cost diffeomorphism. It looks like this. Okay. So we want to refine it. So what we can do is, first of all, we compute the cost Beltrami coefficient of the diffeomorphism, and then we refine the Beltrami coefficient on the finite grid using cubic interpolation. And then from this refined Beltrami coefficient, we reconstruct the diffeomorphism. And this is the reconstructed diffeomorphism. Okay, you can see that the refined diffeomorphism is a smooth refinement that captures the deformation patterns. So here is one application in texture mapping. Actually, this one of the motivation of this project is about texture mapping refinement. So here we have a texture map on the surface given by a cost texture mapping. So you have a texture map, really cost texture map it to the image, and then project it back to the surface. Because the diffeomorphism or the texture mapping is very coarse, then you can see that there is a lot of undesired artifacts on the surface, on the texture. But if we use the refined texture mapping, you can see that the texture is much better. So this is one of the applications in computer graphics, but not quite related to medical imaging. Okay, so this is about how we can use quasi-conformal geometry to do different type of processing of the diffeomorphism. Now, we are interested in looking at whether we can use quasi-conformal mapping or quasi-conformal geometry for 2D shape analysis. Tony has already mentioned quite a number of shape analysis for 3D surfaces. So you may wonder whether we can use this QC geometry to do 2D shape analysis. So the goal of this project is to find a shape signature for 2D multi-connected objects. So instead of looking at simply connected objects, we want to find some fingerprint, some signature for 2D multi-connected objects. So for example, here you have an image of a flower. So it's multi-connected because you have outer boundary and inner boundary. You have a ring surface, so you have an outer boundary, inner boundary. So we want to find some fingerprint, some signature to define this, to represent this signature. So it has a lot of application. For example, medical image analysis is one of them, or shape recognition, classification. So in fact, this project was motivated by a practical problem in vision, in which people are interested in finding an algorithm to do image search. So the basic idea is that, for example, if you want to find a shape using Google search, for example, you want to find a car, then you type CAR, car, and then you have a whole bunch of images given. So, but now if I want to draw a contour, and then I want to find an image closest to the contour that I draw, like this, then in order to solve this problem, we need two things. First of all, we need a very good shape representation, which should be an effective representation of shape and a reliable shape fingerprint that identify an object. And then after that, we want the shape fingerprint to have a lateral matrix, such that we can define a distance between them. Okay, so there are many different algorithms proposed for this problem. So some people use medial axis, some people use shape axis, for example. So most existing algorithms can only deal with simply connected shapes. Okay, and secondly, most existing fingerprint is incomplete in the sense that two different shapes can have the same signature. So this might not be a good shape signature. So as for a complete shape signature for a simple closed curve, Professor David Munford, in his famous paper, he used a conformal approach to represent a simple closed curve, which can capture subtle variability of shapes up to scaling and translation. So it turns out that using the computational quasi-conformal geometry that we propose, we can extend Professor Munford's approach into a multi-connected domain. So I'm going to talk about it. So how can we define a signature for multi-connected shapes? So it is based on two things. The first thing is something called conformal welding, and the second thing is something called conformal modules. So conformal welding is, these two are basically just two fancy terms. The idea is conformal welding is basically a collection of diffeomorphism between unit circles. And conformal modules is just the radii and the center of the circle domain or the conformal domain of the multi-connected domain of the multi-connected objects. So how can we define the signature? So let us look at one simple example. Suppose you have this shape with two fish, Okay, so what we can do is, first of all, we can conformally map region 0 to a circle domain, a punctual disk, and then we can map region 1 to a unit disk, and we can map region 2 to a unit disk. Then we can get a conformal welding, which is the diffeomorphism of the unit circle as follows. So we can map this circle, we can find the composition map of this circle to here and then to here. Then we get a diffeomorphism from a circle to circle. And similarly, we can look at the composition map of this circle to here and to here. And then this gives you a diffeomorphism between the circle. And then what is conformal modules? Conformal module is basically the center and the radii of this circle domain. So this tells you the conformal structure of these multi-connected shapes. So it turns out we can prove that under suitable normalization, this signature is unique in the sense that every shape signature corresponds to a unit shape, and every shape you can compute a unit signature. So let me show you some examples. So here is the two-phase example. So we compute a signature. So here we have two contours, so you have two diffeomorphism between the unit circles. So the diffeomorphism can be represented as a mapping from 0 to 2 pi to 0 to 2 pi. So you have two curves together with the conformal modules. So here we have some other examples. So you have two contours and two levels. So you have two conformal welding together with the conformal modules. So you can see that different shapes has quite different signatures. So here is another example. So for example, we have a Mickey Mouse, two level and three curves. So you have the signature conformal modules. And then you can also do more complicated shapes. So the good thing about this signature is that it inherits a very simple matrix. You can build a very simple matrix to measure the distance. For example, if you have two shape signature, one simple way is that you can compute just the L2 norm of the diffeomorphism, and also of basically this is just a monotonic function, and also the L2 norm of the center and radii. Or we can also use the follow Professor Munford's paper to use the Well-Peterson matrix to compute the distance between them. But there are many different ways to compute a distance. So the good thing for it is that we can now compute a distance between shapes by computing the distance between the signature. Okay, so as I have mentioned,
they have to have the same number of holes, right?
Yes. The topological law has to be fixed. Yeah, that's true. So, of course, one of the very important questions that you may ask is, how can we reconstruct? Because I have mentioned to you that given a shape, I can compute the signature, of course. But now, given the signature, I can reconstruct the unit shape. So theoretically, but can we do so? So actually, we can do so by using quasi-conformal geometry method. So the idea is actually very simple. So if we look at how we compute the signature, it's all about mapping. So given the shapes, so we just compute conformal mapping between them. And then the signature that we have is a diffeomorphism between the inner boundary and also the radii and center of the inner circle. So we know how the conformal domain look like. So the basic idea for the reconstruction is as follows. So what we can do is we can find.
Question.
Yeah.
How do you know where to put the little circle?
Yes. So what we do is, so there's actually there's so.
Because you see, you know the conformal domain, so I know it has two holes, but where does the second hole go?
So we have center and then we have radii.
Right.
Yeah.
Oh, the center. Sorry.
Yeah, we have center and also we have the radii.
Okay.
Yeah.
Sorry.
So okay. So yeah. So the basic ideas to do the reconstruction is as follows. So suppose I have a signature. If I can find a mapping F, okay, such that the inner circle of the conformal domain will be mapped to the desired shapes, then we are done. So now, of course, the question is, given the signature, how can we determine this F? So the basic idea is very simple. The method that we use is that we do a grooving. Because now we know the circle domain, and then we know how the circle, we also know the diffeomorphism between the inner boundary circle. Then we can do a grooving. So the grooving is actually very simple. Suppose, just let us look at a simple case with just this simple shape. So we can conformally map it to a punctual disk. So conformally map this region to the punctual disk F1 and conformally map this region by F2. Then I can define a mapping from a unit disk to a unit disk such that the inner circle will map it to a shape as follows. Okay, so on region A, I just define as F1, the conformal mapping. On region B, I just define as F2 composite with G, where G is the extension map of the signature. Oh, of course. So now the question is, I only have the signature. So obviously, I do not know what F1 is, and I don't know what F2 is. I only know this domain, how this circle domain look like, and I only know what little f is, the signature is. But it turns out that we can compute the Beltrami coefficient from here, because the Beltrami coefficient defined on A is equal to 0, because F1 is conformal. And the Beltrami coefficient of B is equal to the Beltrami coefficient of G, because F2 is conformal. And then the Beltrami coefficient of G can be computed explicitly, because we know F. Then we can compute explicitly. So in other words, by this Brewing process, we know exactly the Beltrami coefficient of F. And then we can solve the Beltrami equation to get F. And after we get F, we get the reconstructed shape. So this is one of the examples that we did. So we have the cat with 2 eyes. We compute a signature, and then we have the conformal modules. And then from the conformal modules and the conformal welding, we construct the shapes using the algorithm that we have mentioned. This is the reconstruct contour. You can see that reconstruct contour is quite close to the original one. So let's look at another example. So this is the 2 fish example that I have used. So I compute a signature and then reconstruct it. So this is the zoomed in view of the signature. So you can see that the blue curve is the reconstructed shape. It is quite close to the original one, except for some smoothing. The reason why there is an error is that we use very low resolution. We only use 3,000 vertex for this whole domain, this domain. So that's why we have error. If we have a high resolution, of course the error will be less. So I think I still have 5.
You have almost 10 minutes. 9.
Oh, 9 minutes. Okay, let me show one more application then. Okay, so another application of QC geometry that we use in medical imaging is to do the surface remeshing. So the goal is to remesh an irregular triangulation mesh. Okay, in other words, we want to approximate a irregular triangulation by a regular triangulation. So the reason is that very often when we get the triangulation mesh, for example, the brain surface, the triangulation is very, very irregular. And it makes it very difficult to do numerical computation on it. Okay, so we really want to approximate the irregular triangulation by some regular triangulation. Okay, so for example, here is one example. We have a hippocampus surface. So this is what we obtain. Okay, so on high curvature region, you can see that the angle of the triangle is actually very small. So as you also ask the question, so when will singularity comes? The singularity will come when we encounter this type of situation. Okay, so we really want to remesh it. So one common technique that we use is to parameterize the surface onto some simple domain, and then we mesh the surface by interpolation onto the and then we draw some regular grid on the parameter domain and project it back onto the surface, and that's how we mesh it. But I call this problem as chicken and egg problem, because for example, if we want to obtain a parameterization, we need a relatively good triangulation. For example, if we want to use the curvature flow method, then if we want to compute the conformal mapping onto 2D domain, the triangulation should be quite good. But it turns out that if we have this kind of triangulation, then we cannot compute the conformal mapping. Okay, then if we cannot compute the conformal parameterization, then we cannot remesh the surface. Okay, so but it turns out that using quasi-conformal mapping, we can solve the problem. The basic idea is based on a composition map method. So the idea is actually not quite difficult. So what we can, so this is based on one simple observation. So suppose we can sort of parameterize the hippocampus onto the unit disk with some Beltrami coefficient mu. Okay. Then what we can do is we can compute a quasi-conformal mapping with the same Beltrami coefficient mu. Then the composition map will be a conformal mapping. Okay. But the question now is, how can we compute a initial parameterization first? Okay, this is very important. So it turns out that we can use something called a thick matrix approach. So it's based on an observation. So if you think about it, we say a triangulation mesh has a very thin angle because it is based on the Euclidean matrix. And we know that all angle structure depends on the discrete matrix, which is the length on each edges. So suppose now I just tell the computer that all the edge length on the triangulation, irregular triangulation mesh to be equal to 1. Okay? Then for human eyes, of course, you look at the Euclidean matrix, then you have a very thin triangle. But for computer, if all the metric is equal to 1, then it look like a equilateral triangle. Okay? And then you can use, and now you can actually run the curvature flow algorithm to parameterize the surface on the 2D domain under this thick matrix. Okay? And then the parameterization on the parameter domain will be some regular triangulation. And then we can compute, and then after we get this parameterization, we can compute a quasi-conformal mapping between the unit bits with the same Beltrami coefficient, and the composition map will be a conformal parameterization. Okay, so here is some example. So we have the same irregular triangulation mesh. So first of all, we just let all the edge length to be equal to 1. Okay, and then to the computer, all triangle will be equilateral triangle. Then we parameterize it conformally using the thick matrix. And then you can see that on the parameter domain, the triangulation is quite regular. You can see that the angle is quite regular. And then now we can compute a quasi-conformal mapping with the same Beltrami coefficient mu. Because here we are using the thick, this is conformal under the thick matrix. But under the Euclidean matrix, this is actually a quasi-conformal mapping with some Beltrami coefficient mu. Then after we compute this mu, we can compute a quasi-conformal mapping with the same Beltrami coefficient mu. Then the composition map will be a conformal parameterization. And then we can use this conformal parameterization to do the remeshing. So the whole idea here is that now we can work on computing quasi-conformal mapping on this regular domain, and then we can get and then we can compute a composition map to get the quasi-conformal mapping. So with this conformal domain, we can draw some regular grid structure, and then project it back to the, interpolate it back to the surface. Then you can see, for example, here is the remeshing result by interpolation of standard orthogonal grid. And here, for example, if you want to preserve more geometry, then on the conformal domain, you can put some regular triangulation according to the conformal factors. And then you can preserve more geometry. Okay? So this is another applications of QC geometry. So I think this is my last slide. I hope this whole bunch of application can show you quasi-conformal mapping has some real application in medical imaging. Thank you very much.
Questions?
So when you're cubically interpolating the Beltrami coefficient, it's like many slides ago.
Yeah.
What are you doing when the dilatation hits too large?
When it's too large?
Yeah, like I mean, are you truncating it when mu is close to 1 or something?
Yeah.
So how does that distort the
If mu is
diffeomorphic? So I mean, the truth is you want to avoid mu switching signs.
Right.
So how are you dealing with that?
But usually given let's say given a diffeomorphism, then the Beltrami coefficient is usually much less than 1.
Right.
So when you do the cubic interpolation, we try to, if it will go beyond 1, then we do some smoothing, like the Gaussian smoothing or something to make sure that. But usually when we do the cubic interpolation, we never encounter this kind of situation that's go beyond 1. Yeah. Yes.
If you look at, so you have some experience now with how the diffeomorphisms compare to the Beltrami coefficient.
Yes.
So if you look at high frequency components of mu, what would that correspond to if I visually on the diffeomorphism?
It's really it corresponds to large deformation and at a small region. For example, if you have some small region with large deformation, then the high frequency region corresponds to this type of deformation.
So it's not the size of mu, it's the high frequency component.
Right.
More questions? Okay, if not, we thank the speaker again.